Hello, AP Physics students. It is time for Unit 6, Lesson 1. And this lesson is all about what we call Hooke's Law. Now, some of you may have seen this a little bit in first semester, depending on who your instructor was. But we're going to hit it real quick again because it's going to play a really pivotal role in what we're going to do in Unit 6. Unit 6 is about simple harmonic motion, but we'll come to that here in a little bit. Now, Robert Hooke was really one of our greatest historical scientists. But he didn't have all of the tools that people like an Isaac Newton or did later. But this diagram on this board is from a lecture he gave in 1678 on what is now become known as Hooke's Law. And it had to do with the behavior of springs. And you can see here's his graph over here looking at this information. It's pretty incredible what all he did. He did all kinds of stuff with microscopes and astronomy, and the dude was all over the place, but really incredible. Okay, so while he said this unit is about simple harmonic motion, we really have to understand Hooke's law to be able to get into that first. Now, Hooke's law says that for a simple spring, like the spring in a ballpoint pen, when you a clicky pen, if you will, the spring will exert a restoring force that is proportional to its extension or compression from its equilibrium position. It's kind of a wordy way to say it, but this equation, which is a pretty simple as equations go, is basically that same sentence, but in equation form, which is part of the reason why we like equations. So the law is often written in these terms, and we're going to understand a little bit more about what this means in a second when I show you guys a simulation. But basically, Fs is the force exerted by the spring in newtons. Now remember that force is a vector. So this force could be to the left or the right or up or down or whichever direction the spring is pointed or oriented. K is the spring constant. We looked at that earlier with elastic potential energy. You may remember the elastic potential energy is 1Fk x squared. So that K is that same K, the spring constant. And X is the displacement. So it's how much is the spring compressed or extended, okay? Now, this right over here, this is this same expression, but now it's in terms of an absolute value. So that gets rid of the negative sign. So where does the negative sign come in? We'll look at that here in a second, but I just want to look at the units here real quick. So K is in newtons per meter. X is in meters. Those cancel out and give us a force in units of newtons, which is good because that's the unit for force. So as we go forward, what's the deal with the negative sign? Well, the negative sign is all about direction. Okay, our force and displacement are both vectors. And so if we take a look at this right here, and let me go to a simulation. I've got a still picture, but let me go to a simulation and go here. So what I've got is a spring, and then I've got a device here that can extend or compress that spring. And so what I can do is I can take that and extend it or compress it. And I want you to notice that there are two forces being shown here. And so I want to be real careful about these forces. There is the force exerted by the spring and the force exerted on the spring. So this is the applied force. This 64 newtons is the applied force. That's how much force I've applied to stretch this spring. That's how much force it took me to stretch it this far. If I want to stretch it farther, it takes a bigger and bigger amount of force to do that. It's not just a constant force that keeps it moving. I need a bigger and bigger force for each meter that I want to stretch this. So in this case, I'm applying a force of 86 newtons, and the spring is responding with a force of 86 newtons. And so we stay in equilibrium here, in new equilibrium. Basically everything is balanced, and we've stretched a distance of 0.429 meters. Here's our spring constant, here's our applied force. What Hooke's law says is a couple of things. One, if I were to double the amount of force, so here's 50 newtons, and it's about 0.249 meters. If I were to go to 100 newtons, it's double that distance. And so what it says is the force is proportional. If I go negative 100, if I push with 100 newtons, then it compresses a distance of 0.5 meters. And so what that means is that the force and the distance are proportional to each other. And the force exerted by the spring is opposite the direction of the deformation. So if the spring is stretched, then the spring is exerting a force back towards the equilibrium position. If the spring is compressed, it's trying to expand back out to the equilibrium position. The spring constant simply increases the amount of force you need to stretch it. So if the spring constant is big, we need then that same 100 newtons of force is not going to stretch or compress it very far. If I make this 1,000, then even when I go up to my maximum force, I haven't stretched it very far. As this drops down, that increases the distance that same force will stretch it. This is a weaker spring. So 100 newtons will stretch it a whole meter. 100 newtons will only stretch this spring a tenth of a meter. Okay, so that X, that negative sign, simply means that if the displacement is in the positive direction, the force exerted by the spring is in the negative direction. So if X is negative, the negatives cancel and this is positive. If X is positive, then this negative makes the force negative. K, we'll see this again later, K is never negative. K cannot be negative. K has to be positive. That's why we call this force a restoring force. It's always trying to move back to equilibrium. It's trying to restore equilibrium again. So if we stretch it, it wants to compress. If we compress it, it wants to stretch. So it's always trying to get back to sort of home. All right, so let's say we've got this spring right here. We've applied a 14 Newton force. It's replying back with 14 Newtons. And it's caused it to stretch a distance of 0.07 meters. So that 0.07 meters is the distance from the equilibrium position to where the end has been stretched to. So I want to know, based on this, what is the spring constant of this spring? What's the value of K? I'll give you a second to figure that out. Well, we've got our equation up here that the force exerted by the spring is equal to negative Kx. I'm going to rearrange this and make this K equals negative F over X. Now, a lot of times, and even on the equation sheet for the AP test, they'll actually use an absolute value here. They'll actually write this as Fs equals absolute value Kx, or sometimes they'll absolute value both sides. The point here is that when they're writing it this way, they're not worried about the direction. They're just trying to get the amount right. So we could do that, but I want to show how the negative sign works here. Realize this equation with the negative sign is written for the force exerted by the spring, not the applied force. So in this case, the force exerted by the spring is negative 14 because the spring is pulling to the left. So there's the negative from the equation and the negative because that's to the left divided by X, which is in the positive direction, 0.07 meters. So the negatives cancel. I get 14 newtons divided by 0.07 meters, which is 200 newtons per meter. That's the value of K for this spring, 200 newtons per meter. Now, ideally, we'd probably want to get more than one data point to be able to do this. Maybe we make a graph or something like we like to do. But based on this one data point, it's 200 newtons per meter. Okay. All right, so if I were to take this same spring, 14 newtons stretched it that distance. If I were to apply 28 newtons, I would get twice the stretch. If I were to double it again, I double the distance again. That's what being proportional means. If instead I were to compress it a distance of 0.07, now the spring pushes to the right. And I know I'm saying the same thing several ways. Sometimes it helps to hear it multiple times. But either the force exerted by the spring is negative or X is negative. But they can't both be negative. And K cannot be negative. So if we're going to write the equation this way, and we'll see more about this as we go on, we just have to realize either the force is in the negative direction or the displacement's in the negative direction. One of those two has to be true. All right, given the information in the diagram below, what magnitude of force will be required to compress this spring a distance of 0.228 meters? So we know that 53 newtons caused it to stretch 0.133 newtons. How much force will we need to compress it a distance of 0.228? And I want you to notice we're talking about just magnitude here, so just the amount. We're not worried about the direction. So go ahead and find the value of that force that would be required. So the way that I would approach this is to rewrite this as K equals F over X. But I'm looking at two different values, and I'm going to go ahead and absolute value this just so we don't have to worry about direction. And F2 over X2. So basically, we know that K for the spring doesn't change. So if K is F over X, then if I change to a new distance, the force should change to compensate. And because they're proportional to this K, which is called the spring constant, or sometimes called the proportionality constant, then that means that this ratio has to be the same. And so that means that 53 over 0.133 newtons over meters is equal to F2 divided by 0.228 meters. And now I will tell you, sometimes people will go equals and tell me what F2 is, but you're not telling me what F2 is, you're telling me what F2 over 0.228 is. So you've got to start a new equation. F2 equals, comes out to be about 91 newtons, give or take. So here's that demonstrated here. So notice that the force exerted by the spring has switched directions because we compressed it, but basically it's proportional, okay? The force didn't quite double, and so the distance didn't quite double either. But it's about twice the force, it's about twice the distance is a rough estimate. So yeah, a lot of times we write it with the negative. So just to sort of clarify here, sometimes we write it with the negative sign if we're talking about the force exerted by the spring, and we talk about it without the negative sign if we're talking about the force applied to make the spring stretch. Again, for the most part, it's just the amount that we're concerned about. But sometimes we do want to pay attention to that direction too, so we want to be careful. All right, now, as you know, in AP, we love to do some graphs. So we want to talk about graphs here for just a second. So when we graph Hooke's law, because force and displacement are proportional to each other, we get a proportional graph. And a proportional graph is just a straight line that runs through the origin. And in this case, the slope of the line is equal to the spring constant. So if you look at this graph over here, here's the displacement on the x-axis and the applied force. That makes it just F equals kx and not negative kx. And we get this line here that runs through like that. So I want to look at this in our simulation. Here we go. So what I've got here is, again, I can go ahead and take this and displace the graph, displace the spring. And you can see on the graph above how I got a certain force causes a certain amount of displacement. If I stretch this further, the amount of force increases and increases proportionally. So zero displacement is zero force. Negative displacement is a negative applied force. Okay. And then I'm not going to worry about that for now. And if I increase the spring constant, we increase the slope of the graph, so that the same amount of force doesn't stretch it as big of a distance. So it takes a bigger, a bigger amount of force to go the same distance in this case. So for this one, the slope would be 400 newtons per meter, whereas here the slope would only be 100 newtons per meter. So that slope there is going to be equal to the spring constant. If I write this way, with force on the y-axis and displacement on the x-axis, convenient, then the slope is equal to the spring constant. All right, so let's say that we have a force applied to a spring and the force exerted is measured and plotted versus displacement of the end of the spring from its equilibrium position. What is the force constant of the spring? So go ahead and find the value of the force constant for this spring. Well, this is really just K equals F over X again. And because we're talking about the applied force, the negative sign doesn't have to be there. But if you like, do we have the negative? Do we not have the negative? Just put an absolute value on it. We're only worried about the amount. Plus K has to be positive anyway. So we're all good. So F over X. So our force is, you can call it negative, but we're going to absolute value it anyway. 250 newtons divided by 0.809 meters. And that comes out to be roughly 310 newtons per meter. So that K value is about 310 newtons per meter, give or take. Okay. All right. Now, there are different ways to draw this graph, but they boil down to the same thing. So this is drawn in terms of the applied force. And so if we stretch in the positive direction, it's because we applied a force in the positive direction. This is written in terms of the force exerted by the spring. So if the displacement is positive, the force exerted by the spring is negative, but it's the same slope. And this is if we write it as the absolute value, which a lot of times they do. Same slope. Okay. Here it's a negative slope and a positive slope, but K itself is positive. They're just looking at the amount of the force. Okay. So it's a little bit weird, but it's okay. It's all the same thing. All right. Now, let's take a look at this. The work to displace a spring. So the work to stretch a spring would depend on the force exerted and the distance displaced. However, the force is increasing. So as we go, we can't just multiply the maximum force by the maximum distance. So if you look at this graph, it took 200 newtons of maximum force to stretch a spring 0.80 meters. But if work is just force times distance, if we're going in the same direction, then why isn't the work equal to just 200 times 0.8? Well, the answer is because the force wasn't 200 the whole time. Here it was like 2. Here's like 100. Here's like 150. And so the force was increasing. So we can't take the force at the end and divide it by and multiply by the distance. We have to take the force at each individual point multiplied by the distance, but that force is constantly changing. That's where calculus comes in, although there's kind of a simpler way. As it turns out, if anytime you have a relationship that is this quantity multiplied by this quantity, then what you're really just finding is the integral. You're multiplying the vertical and the horizontal axis to get that integral. So let's take a look at this graph right here. And I want to know the work done, the work that was required to be done to stretch this spring. So if this is our force and that's our displacement, how much work was done to stretch this spring? Okay, go. Well, as we said, the work is equal to the area because it's force times distance. So that area is 1/2 base times height. So that's 1/2 of the base, which is 0.8, multiplied by the height, which is 200. And that comes out to be 80, and the units of work, in case you've forgotten, are joules. So 80 joules. Number 5, what is the spring constant of this spring? So for number 5, what is the spring constant of this spring? I'll give you a second. So K is equal to F over X if we're talking about the applied force, or if you can't remember, just absolute value it to be safe. So that's equal to 200 divided by 0.8. It took 200 newtons to stretch this 0.8. So that force goes with that position. So 200 divided by 0.8 is equal to 250 newtons per meter. And then finally, number 6, how much elastic potential energy is stored by this spring? So just in case you've forgotten, I'll be friendly. The elastic potential energy stored by a spring is 1/2 kx squared. Go ahead. Whoa, that is 80 joules. Here's why. The energy stored by the spring, it didn't just get it. It got it because we did work to stretch the spring. If we did 80 joules of work to stretch the spring, it now has 80 joules of potential energy stored inside of it for an ideal spring in our ideal situation, no friction or anything like that. So it has 80 joules of elastic potential energy because we did 80 joules of work. Whoa, that is weird. I mean, that's kind of weird that this area is 1/2 base times height and it's 1/2 kx squared. How does that work? Because base times height doesn't have a squared in it. Well, the reason is, since work is area, and that area is 1/2 force times distance, but the force is k times distance, then if I sub in kx for the force, and then multiply it by the x for the distance, I get that. See, force and displacement aren't independent of one another. And so the displacement not only affects the work, but it also affects the force. So that's why it ends up being squared. And that's equal to the elastic potential energy stored by the spring. So if we go back to our simulation, that area right there, so notice that if I go every centimeter I move, not only do I increase the energy, but I increase the energy by an increasing amount. This centimeter doesn't add as much energy as this centimeter does. If I increase the spring constant, it's a stiffer spring, which means it takes more force and thus more work to stretch the spring. And the spring stores more energy with a larger value of K. Now I'm going to ask you this question. Which would affect the elastic potential energy more? Doubling the spring constant or doubling the displacement? Well, doubling the displacement, because the formula for elastic potential energy is 1/2 kx squared. Doubling K doubles the elastic potential energy, but doubling X gives us 4 times the elastic potential energy. All right, I know there's a bit of a long lesson on Hooke's law there, but it's not that it's complicated. It's just that sometimes when things are a little simpler, the AP test likes to make them complicated just to make up for it. So basically, you should be ready to complete AP Physics Unit 6 homework quiz number 1. Remember that Hooke's law relates the force exerted by a spring with the displacement of the spring. The equation Fs equals negative Kx, that's the force exerted by the spring, is opposite the direction of the displacement. That's what the negative sign means. But K is positive. Ooh, I didn't close that parenthesis, yuck. A force displacement graph has a slope that is equal to the spring constant. The area under a force displacement graph is equal to the work required to stretch the spring and the potential energy stored by the spring. Good luck on homework quiz number 1. Bye, guys.